Okay, so now we have both contributions, that is contribution coming from in that linear combination of A and B, that is contribution coming from the spherical Bessel function and the contribution coming from the Neumann function. That is when B is not equals to 0, that is what we are interested in. That is we want to compare this A and B because the information about scattering is all contained in BL, that is B sub L. So now since we have this, so the linear combination, which is basically linear combination of these two functions at the asymptotic region, can be obtained by substituting the values of JL and NL, yeah, into the equation, and then the resulting equation जो हो जाएगी वो क्या हो जाएगी? Uh, so we can write here. So uh, this 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 result, which result? That is the result from the Neumann function in can be substituted in a combination linear combination, i.e. that linear combination is, you remember जो हमने शुरू में लिखा था, A sub L J sub L of K R, which is the first part, plus B sub L, and then the Neumann part and L of sub NL N sub L of KR. So this was the in fact the linear combination um, at the asymptotic region. एसिम्प्टोटिक रीजन का मतलब है, सो रिमेंबर हमने किसी वक्त आपसे डिस्कस किया था कि we observe the process of interaction at large distances away from the interaction center or the scattering center. So it means that the solution is in the asymptotic region, not at the scattering center. So then the total wave function I R जो है, that would be a linear combination of these two parts. And what is that linear combination of these two parts? So R would be equals to, so this R is approximately equals to A L J L of K R plus B sub L and L of K R. And this is approximately equals to किसके बराबर हो जाएगा? So if you substitute uh, these values of ए सॉरी जे एल एंड एन एल जो हमने पीछे निकाली हुई है, तो हमारे पास जो रिजल्टिंग इक्वेशन आएगी, दैट वुड बी सम इक्वेशन जिसके अंदर ए माइनस आयोटा बी अगर हम कॉमन ले लें, और सिम आफ्टर सिंप्लीफिकेशन द रिजल्ट वुड बी आयोटा के आर माइनस एल पाई बाय 2 माइनस ए प्लस आयोटा बी, एंड रिमेंबर यहाँ पर मैं सब एल लगा दूं, and this is important because they represents the angular momentum E minus iota k r minus L by 2, and this whole factor, yeah. And so it means that अगर मैं common ले लूं factor, obviously इधर that factor भी होगा जो हमने नहीं लिखा, तो वो factor in fact 1/2 2k आर आयोटा वाला फैक्टर होगा. सो देयरफॉर जो आपके पास इक्वेशन आ जाएगी फॉर द रेडियल पार्ट, दैट वुड बी इन फैक्ट ए प्लस आयोटा बी सब एल कॉमन ले लूं दोनों साइडों पर, तो दिस इज 2k आर आई, एंड देन द फैक्टर आ रहा होगा ए माइनस आयोटा बी एल अपॉन ए प्लस iota b sub L. Yeah, this is some common factor e to the power iota kr minus L pi by 2 minus e to the power minus iota kr minus L pi by 2 and this factor. Yeah, so इसका मतलब है कि ये जो आपके पास है ये factor. This is the uh, some arbitrary normalization constant. Yeah. This is again, this is the outgoing or scattered wave, which is outgoing or scattered wave, uh, and this in fact is the incoming, अच्छा, in unit magnitude, unit. So normalize कर लिया है, so that would be some unit magnitude. So similarly, this is incoming wave again, also in unit magnitude, because the wave functions, the corresponding wave functions, they are basically in fact normalized in unit. अच्छा, ये ख्याल रखिएगा। अच्छा, गौर से अगर देखें तो दिस इज इंटरेस्टिंग टू नोट हियर कि these are some sort of basis functions. Yeah, so there are two bases for a scattering process. One of the basis for scattering process is the incoming wave, and the other basis function is the outgoing wave. So these basis functions, and you know the properties of these basis function, that is they are orthogonal. That is, they obey the orthogonality condition, that they have unique eigenvalues. And दूसरे ये कि in order to specify the characteristic of these wave function, we basically make them normalized. That is, we have this orthonormal function. So these basis functions, which are the incoming wave function and the outgoing wave and the incoming wave, they are basically orthonormalized. Yeah, that is, they are orthogonal and normalized, and so that's why they are called as basis functions. So in our experiment, these are the basis function. Okay, so that is some comment or side note about normalization. But then अगर हम गौर करें, सो यहाँ जो क्वांटिटी कोफिशिएंट की सूरत में फर्स्ट टर्म के अंदर आ रही है, दैट इज द क्वांटिटी जो जिसको हमने एस जाहिर किया था. सो द क्वांटिटी, इफ़ यू रिमेंबर, हमने इनिशियली कहा था अगर स्कैटरिंग वेव मौजूद हो, देन देयर वुड बी सम मल्टीप्लिकेशन विद सम फैक्टर, जिसको हमने एस ऑफ एस 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 सब एल कहा था, एस सब एल ऑफ के, दैट इज सम स्कैटरिंग मैट्रिक्स. एंड सो नाउ वी नो व्हाट इज एस सब एल. एस सब एल ऑफ के जो है, दैट इज इन फैक्ट ए सब एल माइनस आयोटा बी सब एल over A sub L plus iota B sub L, yeah, is of unit magnitude. Unit magnitude, obviously normalized, and then it represents basically the uh, and represents the scattering effect. And this, if there is no scattering, then this factor S sub L of k would be किसके बराबर, 1 के बराबर हो जाएगा, and would be equal to 1, i.e. S sub L of k equals to 1. कब? when when we say, or rather if there is no scattering. Yeah, so अगर कोई scattering नहीं है, so this would be something like this. So So it's a deviation from one, and the deviation one from one in this case, if there is some scattering present, then the deviation from one would show the scattering effect. Yeah, and जैसे मैंने आपसे पहले कहा, it is also called as scattering matrix or S matrix, and it is typically related in terms of some phase shift. That is, there is a change in the phase angle. So we could write. So it is a deviation from one in case of scattering. Yeah. So if there is that scattering, then it would be a deviation from one, and this is in fact known as the S matrix. It is known as scattering matrix or S S matrix, and is physically written in terms of phase shift, that is delta sub L of k, and this is written as IE. कैसे हम लिखते हैं? If this is in terms of the phase shift, then this is basically written as uh, S sub L of k. So this is delta, yeah. So S sub L of k, which is equals to e to the power 2 iota delta L of k. So this is S, ये S है, that is the S matrix, और ये जो है, this quantity is phase shift. सो ख्याल रखिएगा, इसको दोनों को डिफरेंशिएट हम कर, एंड देन जो कॉम्प्लेक्स रिलेशनशिप है बी और एल के दरमियान, वो क्या हो जाएगी? देन यूजिंग द कॉम्प्लेक्स नंबर relation, that is tan theta, tan this phase shift quantity delta is equals to किसके बराबर होगा? that would be minus b sub l of k divided by these quantities for complex numbers. ये complex variables जब आपने किए थे वहां से आपको मिल रहा है, and so this would imply that delta l delta sub l is equals to tan inverse with a minus sign here, uh, b l of k upon a l of k. So in fact this is the quantity जिसको आप फेज शिफ्ट एंगल कह रहे हैं. सो देन अगर मैं सब्स्टिट्यूट कर दूं, यानी इसकी वैल्यू, ये जो वैल्यू है ये हमने कहा था a माइनस आयोटा बी अपॉन a प्लस आयोटा बी. सो दैट वुड देन, इफ अगर मैं इसके अंदर सब्स्टिट्यूट कर दूंगा इस इक्वेशन के अंदर, तो ये क्या हो जाएगी? सो दिस इज, सिंस s सब l ऑफ k वो बराबर था a माइनस आयोटा b विथ सबस्क्रिप्ट डिवाइडेड बाय a सब l प्लस आयोटा b l, एंड द अदर डेफिनेशन जो हमारे पास आ रही है वो फेज शिफ्ट की सूरत में आ रही है, दिस दिस डेफिनेशन. सो हम इसको क्या कर सकते हैं, वी कैन इनफैक्ट always substitute or then simplification. So after substitution and subsequent simplification, this is S. Simplification, you would have A sub L minus iota B sub L, which is equals to under root A sub L square plus B sub L square e to the power iota delta L. So you can always uh, think about this factor. तो आप अगर substitute वगैरह कर देंगे इसके अंदर, so you would have R, which is almost equals to under root A L square plus B L square whole divided by 2 iota k r. ये आप simplification करने के बाद जो हमारे पास equation आ रही है, which is e to the power iota, which is k r minus L पाई बाय 2, और वो जो e के साथ डेल्टा पार्ट है, डेल्टा सब एल, दैट इज सब एल, दिस क्वांटिटी माइनस ई टू द पावर माइनस आयोटा के आर माइनस एल पाई बाय 2 और प्लस डेल्टा एल, एंड दिस इज होल closed. So this is in fact that radial part. और अब अगर हम इसको सब्स्टिट्यूट कर दें, सो दिस इज द वेव फंक्शन जो हम इनफैक्ट यहाँ पर कैलकुलेट कर रहे हैं इन द प्रेजेंस ऑफ, सो इसको बॉक्स कर दें, इन द प्रेजेंस ऑफ द पोटेंशियल v of r. Yeah, so what we started with the radial part. So initially the radial wave function जो था, if you remember, that was r, which was in fact u k L of R, some normalized function divided by R, and this was equals to some constant times sine function, sine of kr minus L pi by 2 plus delta L. And so you can see here, ये जो ये पूरा पार्ट है, अगर मैं इस 2 आयोटा को नीचे डिवाइड कर दूं तो दिस वुड बिकम दिस पार्ट दैट, एंड डिवाइडेड बाय के आर. So this is in fact divided by kr. So so in fact in an asymptotic region, यानी दूसरे लफ्जों में हमने उसी एक्सपोनेंशियल फंक्शन को in terms of sine. So what we can think about this, that is, this is intuitively or literally the wave function which suffers a phase shift. Yeah, so why? Because we have this quantity in the phase factor as delta sub L. Yeah, and so this is some quantity, this is actually a quantity which is representing the scattering cross section, or in fact it basically represents the distortion. So one would say that this is intuitive, in some intuitive manner. So literally the wave function, that is this R wave function, the wave function really only suffers a phase shift. In a sense, when we say in a sense, the scattered wave are just delayed और एडवांस्ड एडवांस्ड कंपेयर टू द इंसिडेंट waves. And obviously, in the absence of scattering potential, basically delta L क्या हो जाएगा, सिफर हो जाएगा. So in the absence of uh, scattering scattering potential, डेल्टा एल किसके बराबर हो, डेल्टा एल सिफर के बराबर हो जाएगा. सो दिस इज समथिंग विच इज इन फैक्ट वेरी इंपॉर्टेंट रिजल्ट जो हमें यहाँ से मिल रहा है कि व्हाट वुड बी द केस अगर जो हमारे पास इक्वेशन आ रही है. सो इन फैक्ट हम इसको कह सकते हैं, जिस जिस फैक्टर को हमने फेज शिफ्ट डेल्टा एल का है, दैट इज इट इज मेजरिंग सम सॉर्ट ऑफ डिस्टॉर्शन ऑफ द रेडियल पार्ट, या. एंड दिस डिस्टॉर्शन ऑफ द रेडियल पार्ट जो है वो बुनियादी तौर पर इस एडवांस और डिलेड वेव फंक्शन की सूरत में हमारे पास आ रहा है. सो वन कुड से ऑल्सो डेल्टा एल is is a real angle which vanishes for all values for all values of L in the absence of scattering, in the absence of scattering potential. आई अगर V सिफर हो, या V सिफर हो, सो इसका मतलब है कि डेल्टा L is called the phase shift, the phase shift of the Lth partial wave. या सो दूसरे लफ्जों में हम ये भी कह सकते हैं कि डेल्टा एल क्या चीज कर रहा है, इट इज इन फैक्ट अ डिस्टॉर्शन इन रेडियल वेव फंक्शन. सो द फेज शिफ्ट delta sub L measures uh, measures the distortion of R sub k L of R from the free solution, from the free solution. And remember free solution क्या था, सिर्फ the spherical basal function JL of R due to presence of the scattering potential, of the scattering potential V of R. So one would say that जो जो फिनोमेना है कुछ इस तरह से होगा, इफ वी कुड प्लॉट. सो अभी हमने कहा था ना कि दे इधर एडवांस और लैग. सो इसको कुछ यूं कर सकते हैं. सो we could think about a wave or we could think about a lag wave. Yeah, so something like this. So in fact we could think about this जो हमने ऊपर बात की ना, कि in in a sense, the scattered waves are just delayed or advanced compared to the incident wave in the absence of a scattering potential. Yeah. So this is something which is a physical or intuitive interpretation of what's going on in some scattering process. Yeah. And so one could write this in this manner as well. Therefore, what what we have now is in fact the solution where we have both terms which are present, and now since psi is only modified by the presence of this delta function, that is the phase factor delta sub L. One want to relate this, in fact, resulting differential scattering cross section with the result which we have obtained now. Yeah. So so one could say now, since psi, the wave function, is only modified. So अगर आप गौर करें, the only modification is because of this factor delta L, modified by the presence of delta sub L. One then uh, wants to relate this with the resulting scattering cross section, resulting differential scattering cross section. यानी दूसरे लफ्ज़ों में अब हमें क्या करना चाहिए? We need to calculate the scattering cross section, differential scattering cross section. So this is what we are interested in finding, and obviously then we have to relate the results which are basically the experimental and the theoretical result जिसमें हमने differential scattering cross section को relate किया था, and finally the term which we would obtain would be that f sub k. Yeah. जैसे हमने बॉर्न अप्रोक्सीमेशन किया था, सिमिलरली यहाँ पर भी हम इसी तरह से करेंगे. So this relationship, that is this relation with the of this presence of this factor delta L to some scattering cross section can be done by writing all waves as expansions in spherical waves. So what we have to do, we have to sum over all those waves, and then we have to insert these factors जो हमने यहाँ पर निकाले in order to sort of get a relationship between delta L and the scattering differential scattering cross section. So uh, we can say, so this can be done by in fact writing all the waves, or rather partial waves. So this can be done by writing all waves as expansions in spherical waves. So what can we do? So for the incoming, so for example, uh, the incoming, say plane waves, वो क्या हो जाएंगे? So plane waves, let's say some direction, and let's say along the z-axis, they could be written as psi, which is approximately equals to e to the power iota k z, and they can be expanded in terms of the spherical waves using azimuthal symmetry, that is independent of the angle phi. So that could be written as, so this is, if this is can be written, if this is e to the power iota k dot r and we are in the z direction, then that would be e to the power iota k r cos theta, yeah, independent of phi, yeah, because we have the azimuthal symmetry, yeah, can be expanded in terms of spherical waves with azimuthal symmetry. Azimuthal angle का मतलब होता है horizontal angle, and when we say azimuthal symmetry, so it is independent of this horizontal angle. That is this factor e to the power iota kz जो है, that is independent of the factor e to the power the factor phi. Yeah, that is the azimuthal angle. So that is kr cos of theta, and this can be written because we are talking about sum of all waves. So all partial waves. So that is we have to sum over L, and that is A sub L. JL is the spherical harmonic of KR, and we have those PL of cos of theta. So what are these factors? ये जो AL है, this A sub L uh, is called partial wave amplitude. Yeah, and since uh, waves with different since uh, since waves with different angular momentum, different orbital angular momentum, L are different partial waves. So named as partial wave analysis. Yeah. And दूसरा factor जो है this PL of cos theta. This is PL of cos of theta. So this is in fact Lth Legendre polynomial. Yeah. So we have these two factors. So the general solution आपको मालूम है वो क्या होता है? General solution is in fact, if you remember, वो क्या था? That was R of R and Y M L of theta comma phi. या ये था. सो यहाँ पर इंडिपेंडेंट ऑफ एजिमुथल एंगल, सो फाई इज इक्वल्स टू जीरो हो जाएगा, एम इज इक्वल्स टू जीरो हो जाएगा, एंड we we have to include for the RL as the spherical basal function, but including origin. So including origin का मतलब that is the start of the scattering process. So we have R of R, which is approximately equals to J sub L of K R. Yeah, so इसको हम, and for azimuthal symmetry azimuthal symmetry के लिए we would say that this y sub y ml और y सबस्क्रिप्ट के अंदर ही दोनों भी लिख सकते हैं y 0 l, which is in fact the L of cos of theta. Yeah. सो यहाँ पर हमने आपको याद होगा हमने बात की थी, दीज आर द बेसिस फंक्शन, सो वी कैन राइट द नॉर्मलाइजेशन इंटीग्रल. सो यूजिंग for these polynomials PL of cos of theta. So using normalization integral, क्या हो जाएगा, दैट इज -1 to +1 dx p sub l of x p sub l prime of x. x का मतलब ये cos theta, yeah. Then this is equals to 2 upon 2l plus 1, 2l plus 1, and Kronecker delta function L L prime. So this is Kronecker delta function L L prime. So if L is equals to L prime, then this would be equals to 2 upon 2L plus 1. And if L is not equals to L prime, then that would be equals to 0. That is the normalization integral would be 0. So one can find, and with the help of this normalization integral, you can find the values of these coefficients AL, जिसको अभी हमने partial wave amplitudes कहा था. So using normalization function, one can find coefficients A sub L, which are basically partial wave amplitudes, partial wave amplitudes, yeah, in the usual manner. जैसे आप क्वांटम मैकेनिक्स में यूजुअल मैनर, इन द क्वांटम मैकेनिक्स यूजुअल मैनर आई कौन सा, बाय टेकिंग इन अ प्रोडक्ट, बाय taking inner product of the two inner product of these two orthonormalized polynomials, inner product. So इसकी इस तरह से आप बेसिकली एम्पलीट्यूड्स निकाला करते थे, इफ यू रिमेंबर इन योर क्वांटम मैकेनिक्स क्लासेस. सो वी हैव देयरफॉर क्या हो जाएगा, -1 to +1, एंड दिस वुड बी अ फोरियर ट्रांसफॉर्म of the Legendre polynomial. Fourier transform, that is, we multiply the Legendre polynomial with the direction in which the wave is propagating, which is e to the power iota k r. And so when you multiply this quantity, जो आपके पास आएगा, and using the normalization integral, so क्या हो जाएगा, so this would be I so this would be iota k r pl of x का मतलब pl of cos of theta, and this would be equals to a sub l j l of k r dot into 2 upon 2l plus 1. Yeah, so this is in fact the condition, that is, uh, one needs to do the Fourier transform. This is basically the Fourier transform of Legendre polynomial. So that is uh, to find values of a sub l, one needs to